Okay, this is part 2, unit 8B, looking at doubling time and half-lives. So earlier we established that when we're calculating double times, that right here, the new value is the initial value times 2 to the time period divided by the doubling time. So if we want to find out how much of a factor we are growing by, we're looking at this right here, 2 to the time over the doubling time, that ratio. So when we look at, in this question, we have the number of cells in a tumor doubles every 5 months. If the tumor begins with a single cell, so its initial value is 1 cell, how many cells would there be after 3 years and after 4 years? So in this case, the amount we have, so the new value will be the initial value. We start with 1 cell times 2, and this is raised to the, and notice that the doubling time is in months, and the times we're looking for, the time period, is in years. So we need to make sure that we change 3 years to 36 months divided by the doubling time of 5 months. And this will give you, and I should say, approximately 147 cells. So after 3 years, that 1 cell will have multiplied into 147 cells. Now if we go after 4 years, okay, it's going to follow a very similar structure. The new value will equal 1 times 2 to the 48 months, because again we need to be consistent with our units, over the doubling time of 5 months. And this is, and again I should say, approximately 776 cells. So you can see the growth that would take place after 3 years and after 4 years for this tumor that doubles its cells every 5 months. So that's how you would look at doubling when we're given an amount of time and that doubling time rate. Okay, now exponential decay is going to follow many of the same properties. However, when the quantity decreases by the same percent in every fixed period of time, so for example by 20% every year, when we're talking about a decay, because we're decreasing. In this case, the value of quantity repeatedly decreases to half of its value, with each halving occurring at a time called the half-life. And I'm sure many of you have heard of this term, half-life. Now you may have heard of it applied to radioactive materials such as uranium and plutonium. Those are some of the most commonly reported and researched radioactive materials. So when we look at plutonium-239, has a half-life of about 24,000 years. To understand the meaning of half-life, so we suppose that you have 100 pounds of plutonium and it's deposited in a nuclear waste site. The plutonium gradually decays into other substances as follows. So in the first 24,000 years, or one half-life, the amount declines to half its original value, or half of 100 pounds, so it's down to 50 pounds. Again, that's 24,000 years. In 48,000 years, so that's 2 half-lives, then it declines by a factor of 1/2 squared, or 1/4. So we have 1/4 of 100 pounds, which is 25 pounds. And in 72,000 years, which is 3 half-lives, then we take 1/2 raised to the 3rd power, which is a factor of 1/8, and we'd have 1/8 of the original amount, which is 1/8 times 100, or 12.5 pounds. So that hopefully gives you an idea as to how these half-lives work and how we can see what factor we're decaying by over certain periods of time. Okay. Now we're going to generalize this as we did earlier with the doubling, and I'll just highlight below here. But after t time, an exponentially decaying quantity will have, with a half-life of t sub half, decreases in a factor by 1/2 of t over t halves. So the new value is related to the initial value starting at time 0. So we get new value is the initial value times our factor of 1/2 for half-life to the t divided by t sub half. So if we look at this a couple applications here, We have the half-life of a drug in the bloodstream is 4 hours. So that would be T sub half is 4 hours. What fraction of the original drug dose remains in the bloodstream in 24 hours and in 48 hours? So I'll call it part A for 24 hours. So we're just looking at what factor remains. And so we would take 1/2 and we would raise it to 24 hours with a half-life of 4. So this is 1/2 to the 6th power. And this is a pretty small number, 0.015625. So that's the portion that would remain after 24 hours of a drug that has been in the bloodstream for 24 hours. So very little remains. In part B, after 48 hours, so we would take 1/2 raised to the 48/4 power, which would be 1/2, whoops, got ahead of myself, 1/2 to the 12th power. And this is a very, very small number, so 1/4096, or 0.00024. So it's practically undetectable. It's so small at that point. Well, that would be the portion remaining. So it would the factor that remains would be 0.00024, or 0.00024, yes. Okay, so that's a look at the factors and the portions. Okay, now we're going to go back to this idea of plutonium on Earth. So scientists think that Earth once had naturally existing plutonium, 239, and let's suppose that the Earth had 10 trillion tons of this plutonium-239 when the Earth was formed. So given that plutonium's half-life is 24,000 years and Earth's current age is estimated at 4.6 billion years, how much would remain today? And then we're going to use our answer to explain why plutonium is not found naturally on Earth. It's not a simple thing to find. So if we look at this, our initial value is 10 trillion tons. So to give us 10 trillion, so there's billions, millions, 100,000, and then our hundreds. So there's 10 trillion, and we're times it by our half-life, raised to the, in this case, 4.6 billion years is how old the Earth is. So 4600. So there's millions and 100,000s and hundreds. Then divide that by the half-life, which is 24,000, and this is approximately 0. It's pretty much not traceable. And so when we look at that, given the half-life and the estimated time that the Earth has existed with its current age of 4.6 billion years, even though it's estimated that there was about 10 trillion tons found on the Earth, after so much time, it is estimated that the majority has broken down. So, I mean, mathematically, 0, obviously we're finding some on the Earth, but it's negligible. It's so small, and that's why it's so difficult for us to find, and it's not just something that we're naturally digging up in the Earth. Okay, let's see. I got enough time here. So we're going to look at a different question from Yucca Mountain. So the U.S. government spent nearly $10 billion planning and developing a nuclear waste facility in Yucca Mountain, Nevada. Well, the project was canceled in 2011. Now, the intent had been for the facility to store up to 77,000 metric tons of nuclear waste safely for at least 1 million years. So our time and our amount are right there. Suppose it was successful and stored the maximum amount of waste in the form of plutonium-239 with a half-life again of 24,000 years. How much plutonium would remain after that 1 million years? So we'd start with 77,000 metric tons, times it by our half or our 1/2, and this would be raised to the 1 million years divided by 24,000 years, and this is approximately 2.20 times 10 to the minus 8, and this is in metric tons. And oops, spelled that wrong. Metric tons. So after a million years, it would virtually be untraceable. Again, it's such a small number, but again, that's looking at a million years to break it down to untraceable rates there. And so hopefully you can see the power that we have here as we look at this idea of half-life and things breaking down. So lastly, what I want to do is just introduce. There's not going to be any problems on these, but the exact formula for finding doubling time and half-life times, and we'll get into this more in the next lesson. But just as an intro, for an exponentially growing quantity with a fractional growth rate, and again we'll talk more about this in the next one, the fractional growth rate of r, the doubling time is log base 10 of 2 divided by log base 10 of 1 plus r. And the units of time used for this, for t doubling and r, must be the same. So if you're in years, you got to be in years for one, you got to be in years for the other, and or days and days, and so forth. So those have got to match up, month for month, day for day, or whatever the case may be. Similar to that, for an exponential decay quantity, in which the fraction decay rate is r, the half-life is just going to be negative log base 10 of 2 divided by log base 10 of 1 plus r. And again, note that those units must be the same. So we will get more into that in Unit 8C, but that wraps up Unit 8B for us. If you have any questions, please do not hesitate to let me know.